In today's video, we'll be discussing synaptic integration. After watching this video, you should be able to do the following things. First, you should be able to identify an excitatory versus inhibitory neurotransmitter based on how it changes the postsynaptic membrane potential. And second, you should be able to understand how multiple synaptic inputs sum to produce a response in the postsynaptic neuron. In some ways, you can think of a neuron as speaking in a binary code like a computer. It's either firing an action potential or not firing an action potential. To determine whether the neuron should fire an action potential, it has to integrate the many thousands of synapses on its cell body and dendrites. If at the axon hillock the membrane potential is above threshold, you'll get an action potential which will be propagated down the axon and cause the release of neurotransmitter. The neuron also speaks in a frequency code. It can fire fast, slow, or not at all. Now, of course, since this is neuroscience and the brain is so complicated, you have a lot of modulation that goes on as well. So with axoaxonic synapses from modulatory neurons, you can change the amount of neurotransmitter released each time. You can have synaptic plasticity, which we'll talk about in the next lecture. But in today's lecture, we're going to focus on how the cell decides whether to fire or not, and how all of the synaptic inputs onto the cell sum to make that decision. As we talked about in the last lecture, neurotransmitters bind to receptors on the postsynaptic membrane and either directly or indirectly cause a change in the membrane potential of the postsynaptic cell. The easiest way to think about this are with the ionotropic receptors. Neurotransmitters bind, an ion channel is open, and ions move either into or out of the cell and change the postsynaptic membrane potential. If the ion channels open cause a depolarization of the postsynaptic membrane, shown here in green, you have what's called an excitatory postsynaptic potential. If instead the ion channels cause a hyperpolarization or decrease in membrane potential, shown here in red, you have an inhibitory postsynaptic potential. These are often abbreviated as EPSPs for excitatory postsynaptic potential and IPSPs for inhibitory postsynaptic potential. By the end of this lecture, you should understand how these will all sum to either get you to threshold and fire an action potential, or to keep you away from threshold and prevent the neuron from firing an action potential. So as we discussed, an EPSP is an excitatory postsynaptic potential. This is a measured membrane voltage change on the postsynaptic neuron. You'll see in your book EPP or end plate potential a lot. This is very similar to an EPSP, with the exception that the postsynaptic cell is now a muscle cell instead of a neural cell. Muscle cells are excitable cells as well, and a lot of the early work on synaptic transmission was done using the neuromuscular junction. So this synapse includes a motor neuron synapsing onto a muscle cell. Now, muscle cells only receive excitatory information, so you will not get any IPSPs on the muscle cell. For our purposes, an EPSP and an EPP work very similar. It just depends which cell type is the postsynaptic cell, either a muscle or a neuron. A neurotransmitter can bind to an inhibitory or an excitatory receptor. An excitatory receptor is going to want to move the membrane potential towards threshold to cause an action potential, whereas an inhibitory receptor will want to move the membrane potential away from threshold and inhibit an action potential. Excitatory receptors either indirectly or directly open ion channels that allow through an ion or ions that have a Nernst potential of greater than threshold. This means that the ion or ions moving through there will want to bring the membrane potential up towards threshold, depolarizing the cell. Sodium channels would be a good example of an excitatory ion channel. Sodium's Nernst potential is very, very positive as compared to threshold, and so if you open a sodium channel, you're going to have sodium ions coming into the cell, depolarizing it towards threshold. Inhibitory receptors, on the other hand, will open up ion channels that allow an ion or ions to flow through that have a Nernst potential of less than threshold. This means that this ion channel is going to want the membrane potential to be below threshold, which will keep the neuron from firing and inhibit it. Potassium and chloride channels are the two most common inhibitory channels. Potassium, as we know, has an equilibrium potential that's well below threshold. You open up potassium channels, potassium is going to leave the cell and cause an IPSP and hyperpolarize the cell membrane potential. The direction of ion movement through any channel depends on what the resting membrane potential is. So let's say our resting membrane potential of that of which a typical neuron, somewhere around -60, -70. Remember, we've calculated at -48. We've used some assumptions. It's a little higher than normal membrane potential. So that means let's set our threshold at around -50. This particular ion channel opens and allows in an ion or combination of ions that have an equilibrium potential of -10. You can tell that because if you hold the membrane potential at -10 millivolts and open up this channel, what you don't see here is that the channel is opening right at this time for all the 9 different traces. You have a flat line. There's no net movement of ions at the equilibrium potential. If you then look at the resting membrane potential or below the equilibrium potential, you'll see what looks like an EPSP. The ions want to bring the membrane potential up towards its equilibrium potential of -10. If you then depolarize the neuron membrane potential above the equilibrium potential for these ions, you'll see what looks like an IPSP, because these ions want to bring the membrane potential back down to -10, their equilibrium potential. So for this neuron, if you open channels that allow ions in that have an equilibrium potential of greater than threshold, that's going to be an excitatory ion channel. It's going to tend to depolarize the cell towards threshold. Alternatively, if the channel that you open allows in ions that have an equilibrium potential of below threshold, that's going to tend to inhibit the cell from firing an action potential because it's going to pull the membrane potential below threshold. Now, interestingly, if you have a situation where if here's your resting membrane potential and there's threshold, you open up an ion channel that allows ions in with a Nernst potential in between them. It's still going to be an inhibitory channel. Okay? Equilibrium potential is below threshold. Even though it's above rest, it may look like an EPSP at a certain point, but if you pull that membrane potential above the equilibrium potential of those ions, for instance, if you sum with an additional excitatory input, then you're going to start to see hyperpolarization, because again, ions moving through that channel would like the membrane potential to be at their equilibrium potential, which is below threshold, which is going to oppose the generation of an action potential. In addition to the evoked release of neurotransmitter, so you generate an action potential in your presynaptic neuron, cause the release of neurotransmitter from your synaptic vesicles, people also notice that there was spontaneous release of neurotransmitter. So if you look here, you see these little blips. They're called mini EPSPs or mini end plate potentials if it happens on a muscle. So these are the spontaneous release of a single vesicle of neurotransmitter. So if you notice, they all have around the same amplitude, and it's quantified for you with this histogram here. The number of mini end plate potentials with a given amplitude, you can see most of the amplitudes of the minis are around 0.4 millivolts. Okay, so the spontaneous release is caused by just spontaneous binding of calcium with synaptotagmin and the release of one vesicle. This also shows you that each vesicle is filled with about the same amount of neurotransmitter, so it'll cause about the same amount of depolarization on the postsynaptic membrane. Similarly, if you take a motor neuron and a muscle cell, you stimulate the motor neuron and record from the muscle, but you place this preparation into a solution with very low extracellular calcium. Okay, so not much calcium can go through those voltage-gated channels. If you stimulate the motor neuron and then you record the evoked response, shown here, you can see that you'll get EPSPs of varying heights. But if you then put them into a histogram again, you'll see that they tend to cluster around multiples of the amplitude 0.4 of the mini that we just saw in the first one. So that means either 1 vesicle is released, 2, 3, and so on. Now, with normal amounts of calcium in the bath, of course, you'll get many, many more synaptic vesicles release. And that'll mean it'll be harder to see these discrete multiples of 0.4. But this experiment was good proof of what's called the quantal release of neurotransmitter. And that is that the amount of neurotransmitter released is proportional to the number of vesicles exocytosed. Okay, so we saw that the mini amplitude is consistent. You release about the same amount of neurotransmitter per vesicle. And with the low calcium experiment, you could see that the EPSP amplitude was an integer factor of the minis. Okay, so this is very good evidence that your neurotransmitter is in fact packaged in those vesicles and released. So now that you understand a little bit more about the changes on the postsynaptic membrane that can happen due to the release of neurotransmitter, let's talk about how the cell decides whether it's going to fire an action potential or not. As we said, each cell receives thousands and thousands of synapses, and they all produce very small changes in membrane potential. And you have to sum all these up to either get to threshold or remain below threshold. There are two main mechanisms of summation. There's temporal summation. So if you have this neuron 1 here, and you stimulate it once, you're going to get an EPSP as shown here. If you stimulate it twice in quick succession, the membrane potential after the first one hasn't gone back down to rest, so if you open the channel again, you'll get additional ion movements, and you'll increase the membrane voltage an additional amount. So this is temporal summation. So an input from the same neuron multiple times of firing will get you a higher change in membrane voltage. You can also have spatial summation. So if now you have 2 neurons, if you fire the first one, you'll get a certain amount of membrane voltage change. Second one, a similar amount. But if you fire them together, they can add up and give you a greater depolarization of the membrane. So now, for a neuron to fire an action potential, the membrane voltage at the axon hillock must be above threshold. So if you have multiple excitatory inputs, or on a single input firing twice, that membrane voltage change has to travel down towards the axon hillock. Okay? And there it gets summed, and the decision to fire or not fire is made. So now the question you might ask is, are all synaptic inputs created equal? Do you just need X number of excitatory neurons firing to get you to threshold? And of course the answer is no. The distance matters. How far away your synapse is from the axon hillock is important. The further away it is, the more that the current is going to decay before reaching the axon hillock. Similarly, the conductance change matters. The number of ion channels that are open can determine the voltage change. So there are some synapses that will cause greater voltage changes than other synapses. Similarly, the driving force for the ion coming through that channel matters. The greater the driving force, the greater amount of current that's going to flow. As we learned in the last lecture, most axodendritic synapses tend to be excitatory, and most axosomatic synapses tend to be inhibitory. In general, axosomatic synapses are more powerful or are weighted more in the final summation in the axon hillock. And this is due to a few reasons. First, the axosomatic synapses tend to be closer than the axodendritic synapses to the axon hillock. Second, they can kind of shunt some of the excitatory current coming down. So if you think about it, if you've got excitatory current coming down from the dendrites, and you have an inhibitory channel open that will tend to pull the membrane below threshold, now that you've pulled it slightly above where it was at resting, you're going to increase the driving force on the ion going through the inhibitory channel. This will tend to blunt the excitatory current coming down and weight the synapses towards the inhibitory synapses. Okay? And if you think about it, this is important because you only want your neuron to fire when you absolutely are sure that you want it to fire. Excess firing can lead to excitotoxicity and death of the cell, and you want to make sure that you're turning on and off your signaling in very discrete ways. So in this way, the cell is set up so that it weights its inhibitory synapses more and only fires when it's absolutely sure that all of its synaptic inputs are integrating to yes, go ahead and fire. That concludes this video. Hopefully now you can identify an excitatory versus inhibitory neurotransmitter based on how it changes the postsynaptic membrane potential. And you also understand how multiple synaptic inputs sum to produce a response in the postsynaptic neuron.